Okay, so today is the first recording for my linear algebra teaching project. And today's topic is vector and vector operation. I know it maybe seems too quick to jump into the content. In the future, I will probably do a class on more like the big picture of linear algebra and maybe give some sense of what it is really. But for now, let's just jump into the content. So firstly, our main actor today is a vector. So let's first define what is a vector. So a vector basically is a tuple of numbers. And don't let the word tuple scare you. Tuple is just a fancy way of saying a bundle of numbers. So this bundle of numbers basically packed some numbers together in a way that will later on will define some special properties on this bundle of or this tuple of numbers, and that is something we call a number. And that's a really abstract way of talking about what vector is. So let's be more concrete and actually talk about talk about some examples. So the first example is this, the vector 1, 2. This is simply one way of writing a vector. And so you have a bracket, and then you write it from top to bottom. So here you have 1 and 2 from top to bottom. And to save space, sometimes we write it like this, using this bracket or parenthesis, and either way works. It's just a way to represent it's a vector. And since there are two numbers in this tuple, we call this vector a two-dimensional vector. And this two-dimensional vector has two components. So those are just some terminologies. So if we want to visualize this 1, 2 in a two-dimensional space, which is represented by x and y axes, the first number here, this is a number on x-axis. And 2 would be on y-axis. So let's actually draw it. So on x-axis, this is 1. So we mark it here. And then on the y-axis, so 1, 2. Here is 1, 2. And that's the end of our vector. And to represent this vector fully, by convention, we draw an arrow starting from the origin, ends at the point 1, 2. So this arrow represents the vector 1, 2. And something else about vector is it doesn't matter where you put the vector. So here we have 1, 2, but it starts at the origin. We can also start the vector at here. We use a different color. So if we start the vector from here, it's the same thing. Again, we count. Starting at here, we move to the right by 1. So it's here. And then we move up by 2 units. So 1, 2. So now we are here. So that's where our vector should end up with. And then we draw the arrow. The arrow is important. Vector is not simply vector is not just a point. It's an arrow that represents it. So it must have a start and an end. And so maybe my drawing and isn't really good, but um, the blue arrow and the green arrow in this graph all represent the vector 1, 2. So it doesn't really matter where you start the vector, as long as if you copy this and move this around, and then eventually it can overlap with each other, which in this case it doesn't because my drawing is bad, but technically it should be. As long as you can overlap those two vectors onto each other, then those are the same vector. In this case, it's the blue and the green arrows are all the graphical representation of the vector 1, 2. So that's vector in two-dimensional space. And let's move on to three-dimensional space. So in three-dimensional space, we have one more component. So it's the same thing with the first two. So 1, that's x, and 2 is y, and 3 represents a number. That's the new added component, which is the z component here. So in this case, we have 3 numbers, and each numbers are assigned onto one dimension. So let's plot it and actually visualize it. So let's count. So this is x-axis. So we count 1 since it's the first number. So we mark it here. And then we go find what's the number associated with y-axis. And y here we see is 2. And so we go to find 2 units on the y-axis. So here it's 1, here is 2. So if we draw it now, it should be something like this, because it has to be parallel to the 2 axes. So simply drawing x, y, that would be the point, but that doesn't represent the vector. We still need one more dimension to draw this three-dimensional vector. And the third component lies on the z-axis. So we find 1, 2, 3. And so the third number is 3, and we draw it like this. And so this is the intersection. So this point is the endpoint of our vector 1, 2, 3. And we draw the arrow. Let me actually use my ruler. Okay, much more better. It's a little bit messy because the coordinates line kind of overlaps with it, but I hope you can see it. So this arrow that I just drew is the graphical representation of the vector 1, 2, 3. So to summarize, we can see there is a really interesting kind of like 2 rows of vectors, or 2 different kind of representation of vectors, or we can, to put in a more fancy way, we can say there's a duality of vectors here. And one is more of the numerical aspect of vector, which is just a bunch of numbers binded together. And the other way is to visualize it, to actually draw it in 2-dimensional, 1-dimensional, or 3-dimensional. And there are some way you can go to the higher dimension, but it's really hard to visualize them. So the visualization aspect kind of stop moving or stop working after, or if you go beyond the three-dimensional space. But within the three-dimensional space, we can have a really intuitive idea of how the vectors looks like. So that's the foundation of what is vector and how they can be represented. And now we have our vectors. What can we do with them? There are, for now, basically three things, but you can argue it's only two things because one can be reduced to the other. Or technically only one, but okay. Let's just say three for now. The first is addition. So you have two-dimensional vectors, and you want to add them. So intuitively, how would you go about adding those two vectors? Think about it. Well, for me, the most intuitive way is you just simply add each component. So if we follow that rule, let's look at the first component. So 1 plus 3, we got 4. And then if you look at the second component, so let me actually mark them with colors. So 1 plus 3 is 4. And then if you look at the second component, you have 2 plus 4 is 6. So if we want to formalize it, it would be for a vector, this is how we write vector. So normally it's, if you read the book, like mathematical book, vector is usually written in like bold letters, something like this. But you see, it's not a really good idea if you're writing it. So normally we simply write the letter and then an arrow on top of it to show that it's a vector. And so if, say, we are just in two-dimensional space, so V can be represented. So V is a vector. And V has two components. The first one is V1, and the second one is V2. So don't confuse yourself here. So V with an arrow, this is a vector. And V1, V2, those are all numbers. These are the components of the vector V. So like in the case we just mentioned, like here, 1, 2, those are V1 and V2. But the bracket together is a vector, and that's the vector V. So to formalize it, say we have V plus another vector W. So this is to add two vectors together. And say W, it has two components, which is W1 and W2. And if you add them, the rule is the result would be you simply add each component together. And so here will be V1 plus W1. And then the second component would be V2 plus W2. So yeah, as you can see, it's a different color. This is the first component. Simply add the first row together, and then you add the second row to get a component of your result. So that's how you do vector addition. And since we had a way to visualize the vector itself, we also have a way to visualize the addition, the process of addition. So let me show that to you. So in two-dimensional space, of course, still xy plane. So let's just use our example here, the vector 1, 2 plus 3, 4. So first, let's draw the vector 1, 2. So on x-axis you have 1, on y you have 1, 2, and that's the endpoint. And okay, I'll use my ruler. It's still off by a little bit, but it's good for now. So that's a vector 1, 2. Should probably use a different color, so let me maybe use blue. So this is 1, 2. And then let's also draw 3, 4. So 1, 2, 3. And 1, 2, 3, 4. So it's here. Yeah. And you connect the origin with the end line, and that will be 3, 4. So the operation of addition, if you want to visualize it, there's actually two ways you can do it, but here we will show the easier way. So the easier way is you move one of the vectors, say it's here. Say if we move 1, 2, we want to move its endpoint to where the second vector start point is. So we move all the way until up here. And let me move this away. And now the result of this operation would be now if you connect the endpoint and the origin. So the result of this addition is this green line. And take a guess, what's the dimension of this green line? Or what's the component of this green line? Well, it's two-dimensional since it's on two-dimensional space. But its component, if my scaling is right, here is 4. And then here is 5, 6. So this green vector, its two components is 4 and 6, which is what we calculated. So you can see this really nice overlapping or like duality between the numerical calculation and the graphical representation. And you can do this to three-dimensional space as well, but we won't do it for the sake of time. But the rule is still the same. So here you have subtraction. Subtraction, the reason why I said there's only, like, this is kind of the same as addition is that this is actually equivalent to, so those are algebra. So if you can, so even though it's subtraction, you can say it's add, but then everything in the second vector will become negative and -3. So if you apply the addition rule, this will just give us, so 3 minus 1 is 2, 4 minus 2 is 2, and 5 minus 3 is 2 as well. So we have 2, 2, 2 at the end. But, well, that's just to show you how you can derive one rule from the other one. You can derive the subtraction rule from the addition rule. But next time when you see subtraction, the intuition is you can just subtract each component or component by component. So look at the first component and you say, okay, 3 minus 1 is 2, and then you look at the second component, you say 4 minus 2 is 2, and then lastly you have 5 minus 3, which is 2 as well. So you don't need to go over the thought process of switching between addition and subtraction. So yeah, that's vector subtraction. It's not too bad, right? It's basically you do the normal algebra several times, component by component. So that's adding and subtraction. And then we also have what we call a scalar multiplication. So scalar, what is scalar first? Scalar is, well, it's basically one number. So in this case, the 3 here is, no, that's not what I meant. So 3 here is a scalar. And so here's 3 multiply a vector 1, 2. So intuitively, what would you do? Well, it kind of goes component by component too. So you will do 3 times 1 is 3. And 3 times 2 is 6. Pretty easy, right? So you just multiply, you take that scalar and then multiply that scalar into each of the components. We're kind of distributing that scalar into each component, and then you multiply it to get the result, and that will be 3, 6. So you might ask, what is, so since we have graphical representation for all the other operations, so what about this one? Well, there is a graphical representation for this one as well. So let me mark it. So you have 1, 2, 1, 2, 3, 1, 2, 3, 4, 5, 6, 6, 3. Okay, 2. So we'll find 1, 2, and that's our vector. And then we can also draw 3, 6 this time, using a different color. So 1, 2, 3 here. 1, 2, 3, 4, 5, 6. So it's here. So 3 and 6. That's where it should be. So again, this is not a perfect graph, but if it is a perfect graph, what you should see is this green line actually is part of this, sorry, this blue line is actually part of the green line. Okay, now it's part of it. I coerced it onto it, but okay. So this is actually part of it. And if you take it and duplicate it, or copy it, so let's mark it. So see, So say this is a first end, and then let's move this. Ew. Okay, so now this is a second copy, and then we move one more time. We would have this. So do you see what I'm trying to say? So basically, um, if you multiply a vector by a scalar, like here's 3, you stretch it by 3 times. You extend it, and the end vector, the length should be 3 times the original length. And it's extending in the same direction as it was pointing before. So that's the geometric interpretation of this operation. So since it's already almost 30 minutes, so I don't want to move on to linear combinations. So I guess I'll stop here for today. But lastly, let's just do some really quick recap. So first we defined our main actor, our hero here, vector. And vector is just a bundle of numbers or a tuple of numbers. And we say vectors have this duality of represented by numerical values and by graphical means. And there's a really nice consistency between those two ways of representing, because you can essentially switch one way to the other way if you want. Depend whether you're a visual learner or if you just a math geek. And we also say you can add them, subtract them, and multiply them by a scalar. So if you add them, no matter which operation you do, essentially what you do is you kind of do the same algebra over different components to get the result. And you can do that, as I said, you can add them, you can subtract them, or you can multiply them by a scalar. And they have their own geometric interpretation as well. So I guess that's it from today.